a finished car tire drops from a curing press. Hot, black, and sharply patterned. But the mold did not build it. Before that press closed, the tire had already been assembled from rubber, steel, textile cord, and an air-retaining inner liner. Heat only locked that hidden structure together. Every time you brake or turn, you trust that structure without ever seeing it. And because curing can seal a mistake beneath flawless black rubber, the factory must inspect inside the finished tire without cutting it open. That is what makes tire manufacturing so unusual. A tire is built twice, first through mechanical assembly, then through chemical transformation. Cut one open, and the familiar black ring reveals an engineered composite. Steel belts stabilize the tread. Textile body plies contain pressure and support load. Steel bead bundles secure the tire to the wheel. The inner liner slows the escape of air. Even the rubber is not one material. A modern passenger tire may use up to 12 different rubber compounds, each designed for a particular location and purpose. The tread must resist wear while producing grip. The sidewall has to flex repeatedly without cracking. The inner liner needs very low gas permeability. Rubber around the steel belts must bond securely to metal. Other compounds manage heat, aging, stiffness, and the transitions between flexible and rigid regions. The factory is not searching for one perfect rubber. It is designing several imperfect materials that can work together. That challenge begins with a weakness that once made rubber unreliable. Untreated natural rubber can become soft and sticky in hot weather, then harden when the temperature falls. In 1839, Charles Goodyear found that heating rubber with sulfur and other ingredients made it far more stable. The process became known as vulcanization. Sulfur helps create connections between the long polymer chains inside rubber. These crosslinks limit how freely the chains can slide. The material can still stretch and flex, but it becomes better able to recover instead of flowing apart or remaining permanently deformed. That discovery helped make durable pneumatic tires possible. The modern factory still depends on the same central principle, but the transformation begins long before the tire reaches the curing press. It begins in the mixing room. Natural and synthetic rubber arrive as dense blocks. Machinery cuts them into manageable pieces, and each ingredient is weighed according to a controlled recipe. The rubber enters a powerful industrial mixer, along with fillers, processing materials, anti-aging agents, and other chemicals. Large internal rotors compress, stretch, and fold the material. Friction and mechanical work generate heat as the ingredients disperse through the compound. Carbon black can reinforce rubber, improve resistance to wear, and contribute to its familiar black color. Silica is used in many tread formulations to help engineers balance wet grip, wear, and rolling resistance. Oils and resins influence processing and performance. Sulfur, zinc oxide, accelerators, and related ingredients prepare the compound for curing later. The quantities, processing time, and temperature all matter. A batch can look uniformly black even when something inside is wrong. A poorly dispersed filler or an incorrect ingredient level may affect how the finished tire wears, bonds, flexes, or generates heat. The first serious quality risk therefore appears before the tire has a shape. When mixing is complete, the material emerges as a hot, heavy mass resembling rubber dough. Machinery processes it into slabs or sheets, cools it, identifies the batch, and sends it toward the line responsible for its particular job. One batch may become sidewalls. Another may become an inner liner. Several others may be combined into the tread. The tread begins as chemistry long before it becomes a pattern. Its compound travels to an extruder, a machine that pushes rubber through a shaped opening called a die. A continuous profile emerges from the other side with controlled width and thickness. The basic idea resembles squeezing material through an enormous precision nozzle. The actual process is far less forgiving. Rubber changes as it heats and flows. If the feed rate, temperature, or pressure drifts, the tread profile can become too thick, too thin, too heavy, or dimensionally unstable. Those differences matter. Extra material affects weight and heat generation. Missing material can compromise geometry and durability. The factory must reproduce the same profile consistently across a long production run. Some tread designs combine multiple compounds in one profile. Separate streams of rubber enter a specially designed die and emerge joined together, placing different materials in different parts of the tread. There is no universal three-compound formula. The number and arrangement depend on the performance. The tire is designed to deliver. On some production lines, small rollers apply colored stripes to the fresh tread. These stripes are not decoration and do not improve traction. They form a factory identification code, helping workers and automated systems distinguish between compounds, dimensions, or product specifications. The colors may eventually disappear, but their job is already finished. They helped prevent the correct-looking tread from being sent to the wrong tire. After extrusion, the warm profile passes through cooling and handling equipment. The line controls tension so the rubber is not stretched out of specification. The tread is measured, cut to the required length, and prepared for assembly. So far, the factory has shaped the rubber. Now it has to solve a harder problem. Rubber alone cannot keep a pressurized tire stable under the weight and speed of a moving car. That requires reinforcement. Textile cords made from materials such as polyester, rayon, nylon, or aramid are arranged into a continuous sheet. The sheet enters a machine called a calender, where large rollers coat both sides with controlled layers of warm rubber. The result is not ordinary fabric with rubber painted onto it. The cords become embedded inside a rubber matrix. The textile provides dimensional stability and tensile strength. The rubber holds the cords in position, protects them, and allows the reinforced layer to bond with neighboring components during curing. The coated sheet is cut to the required width and angle. Cord direction is critical because it determines how forces travel through the finished tire. A perfect material cut at the wrong angle is no longer a perfect component. Steel reinforcement follows a related process. Fine, high-strength steel filaments are combined into cords, arranged in sheets, and coated with a rubber compound designed to bond with them. The material will later become the belts beneath the tread. Those belts stabilize the crown of the tire, the region that repeatedly enters and leaves contact with the road. They help control its shape as speed, load, braking, and cornering forces change. The steel-rubber interface is itself a quality risk. Contamination or weak adhesion may be hidden after curing, but every rotation will continue loading that boundary. A second form of steel reinforcement creates the beads. Multiple steel wires are formed into strong circular bundles and coated with rubber. These bead rings fit around the wheel rim and create the foundation of the tire's connection to the vehicle. Shaped rubber around the bead helps manage the transition into the flexible sidewall. The bead region has to remain secure while the material beside it bends. If that connection is wrong, the rest of the tire cannot compensate. The factory also produces the inner liner. Most modern passenger car tires are tubeless. Instead of holding air in a separate inner tube, they use an innermost layer made from rubber with very low gas permeability, commonly based on butyl rubber. The liner, tire beads, wheel, and valve form the pressure chamber. Some air still escapes gradually over time, which is why inflation pressure needs regular checking. Tubeless does not mean puncture-proof, and an ordinary tubeless tire does not automatically repair itself. The inner liner simply allows the tire and wheel to contain pressurized air without a separate tube. At this point, the factory has tread strips, sidewalls, rubberized textile, steel belt material, inner liners, bead rings, and several smaller components. Almost everything required to make a tire is present. There is just no tire yet. More importantly, the parts cannot merely be stacked in roughly the correct order. Every component may pass inspection on its own, and the finished tire can still fail if one layer is positioned incorrectly. Assembly begins on a tire building drum. The exact sequence varies by tire design, manufacturer, and equipment, but a typical passenger radial tire starts with the inner liner. It wraps around the drum to form a cylinder. The rubberized body ply material is applied over it. Its cords will eventually run broadly from one bead to the other, helping the casing contain pressure and carry load. The two bead rings are positioned near the edges. Machinery turns the ply around them, securing the reinforcement to the bead structure. Sidewall components and additional shaped materials are added according to the design. Rollers travel across the assembly, pressing the tacky, uncured layers together and reducing trapped air. Sensors and positioning systems help control alignment and tension. Automation can repeat an operation with extraordinary precision, but it cannot rescue a component that arrived with the wrong dimensions or compound. Every previous stage is now being tested by the assembly process. The result of this first operation is the tire's inner casing. It still looks more like a wide cylinder than the tire beneath a car. The reinforced outer crown is built separately. Steel belt material wraps around a second building drum. Successive belt layers are placed at deliberate angles. Depending on the design, additional narrow reinforcement may be wound over the belt package with controlled tension. The uncured tread is then positioned around this reinforced crown. Now the factory has two major structures. The first contains the inner liner, body ply, beads, and sidewalls. The second contains the steel-reinforced crown and tread. They were built separately because they required different geometry and control. Now they must be joined with enough accuracy to survive thousands of miles of rotation, heat, and deformation. Our transfer ring collects the belt and tread assembly and carries it toward the casing. The inner casing expands outward, changing from a cylinder into a rounded tire shape. As it rises, it meets the crown assembly held around it. The sticky, uncured surfaces make contact. Rollers work across the tread and shoulders, consolidating the layers and joining the crown to the sidewall region. This moment destroys the idea that a tire is poured into a mold. Before the mold has touched anything, the factory has already built the inner skeleton, constructed the reinforced outer crown, and joined them into one assembly. That assembly is called a green tire. Green simply means uncured. The green tire has bead openings, sidewalls, a crown, an inner liner, textile cords, steel belts, and almost all the rubber found in the final product. It looks like a tire, but it cannot safely carry a car. Its surface is comparatively smooth. Its layers are held together mainly by the tack of uncured rubber, and its compounds have not reached their final physical properties. The green tire has the anatomy of a finished tire, but not its material memory. It can be shaped, but it cannot yet survive the repeated deformation of real driving. Everything now depends on one irreversible step. The green tire enters a curing press containing a precisely machined mold. The inner surfaces of that mold carry the negative shape of the tread and sidewall markings. The press closes around the tire like an enormous waffle iron. A flexible bladder expands inside, forcing the green tire outward against the mold while heat and pressure move through the structure. The mold creates the visible features: tread blocks, grooves, sipes, shoulder shapes, brand names, size information, and regulatory markings. Small vents allow air trapped between the green tire and mold surface to escape. Tiny amounts of rubber can enter those vents, forming the thin whiskers sometimes seen on new tires. Those whiskers do not improve grip. They are simply traces left by the molding process. The tread pattern is only the visible result of curing. Inside, the rubber heat activates the chemical system prepared in the mixing room. Cross links form between polymer chains, limiting how freely those chains can slide. The soft compounds become resilient elastomers. They can deform under load and then recover instead of remaining permanently distorted. The steel belts do not melt into the rubber. The textile cords do not disappear. Each material remains structurally distinct. Curing creates the rubber network and bonds that allow all of them to function together. The reaction must be controlled through materials of different thicknesses and composition. Time, pressure, temperature, and formulation have to converge. Insufficient curing may leave rubber without its intended properties. An inappropriate cure can also damage performance. The factory is not heating the tire until its exterior merely looks finished. It is controlling a chemical transformation throughout a complex composite structure. Curing does not create the tire's architecture. It makes that architecture permanent. When the cycle ends, the press opens. The tread is sharply defined. The sidewall carries permanent lettering. The soft green tire has become an elastic pressure vessel capable of supporting load and surviving repeated deformation. A cutaway reveals the result. The inner liner forms the smooth internal surface. Textile cords pass through the casing. Steel bead bundles sit inside the lower sidewalls. Steel belts reinforce the crown, and the tread covers the structure that stabilizes it. The layers have not become one uniform substance. They have become one working system. But the process that completes the tire also creates a final problem. Before curing, many components were visible as they were assembled. After curing, a flawless black surface can conceal displaced cords, irregular belt edges, trapped material, or unwanted spaces between layers. The tire is finished. Its manufacturing history is hidden. Now the factory has to look inside. Visual inspection comes first. The tread, sidewalls, beads, markings, and surface finish are examined for abnormalities. Dimensions and geometry can be compared with the required specification. Appearance alone cannot confirm the condition of the internal reinforcement. X-ray equipment provides the delayed answer. Radiation passes through the tire and creates an image in which denser structures such as steel belts and bead wires can be examined. The system can reveal their position and identify certain abnormalities without destroying the product. Inspection programs vary between manufacturers, factories, and tire types. But X-ray technology gives quality control teams something ordinary vision cannot: a way to examine the structure after opaque rubber has sealed it from view. The tire may also undergo uniformity testing. It is mounted, inflated, and rotated against test equipment. Sensors measure how consistently it behaves around its circumference. A tire can look perfectly round while producing changing forces as it rolls. Small differences in geometry, material distribution, or stiffness may become vibration, noise, or handling problems on a vehicle. Balance and uniformity are related, but they are not identical. Balance concerns how mass is distributed around the tire and wheel. Uniformity concerns how the tire generates force while rolling under load. A tire can be balanced by weight and still contain one region that responds differently from the rest. Manufacturers also perform destructive performance tests during development, validation, and production control programs. They do not destroy every tire. Defined samples are tested under controlled conditions because a tire pushed to failure cannot then be shipped to a customer. In the United States, Federal Motor Vehicle Safety Standard 139 includes requirements involving dimensions, high-speed performance, endurance, low inflation operation, strength, and resistance to bead unseating for new radial tires within its scope. The DOT symbol molded onto a tire is commonly misunderstood. It does not mean a government inspector personally tested that individual tire. It indicates that the manufacturer certifies the new tire as meeting the applicable federal safety standards. No single inspection proves everything. A visual check can find surface problems, but cannot fully reveal internal alignment. An X-ray can show important hidden structures, but cannot reproduce years of driving. A uniformity machine can measure rolling force variation, but cannot simulate every road surface or impact. Destructive tests can push samples through defined conditions, but only those samples experience the full test. Quality cannot be added to a tire at the end. It has to be built into every stage: material selection, mixing, component dimensions, chord angles, layer placement, curing conditions, and final verification. Only then can the separate parts perform their jobs on the road. The inner liner contains the pressurized air. The beads secure the connection to the wheel. The body ply contains pressure and carries load through the casing. Steel belts stabilize the tread region. The tread compound manages grip, wear, heat, and rolling resistance. Its grooves help move water away from the contact area in wet conditions. In a pneumatic tire, much of the vehicle's support comes from pressurized air. The rubber and reinforcement form the flexible container that controls that pressure and transfers its forces. As the wheel turns, each section of tire approaches the road, flattens under load, travels through the contact area, then recovers as it rotates away at highway speed. That cycle repeats many times every second, while the tire is also braking, accelerating, steering, absorbing impacts, and generating heat. No single layer could manage all of those demands alone. Radial construction made that division of labor even more effective. In 1946, Michelin filed a patent for the radial tire, in which the body cords run broadly from bead to bead while a separate belt package stabilizes the crown. The sidewall can flex while the tread region remains comparatively controlled. Different parts of the tire are allowed to specialize. That same principle governs the entire factory. Different compounds specialize. Different reinforcements specialize. Different production lines specialize. Tire building brings them together, and curing makes their cooperation permanent. Return to the finished tire emerging from the press. At first, it appeared that the mold had created it in one dramatic moment. Now that image means something different. The tire began as several chemical recipes. Those compounds became profiles, coatings, sidewalls, and air-retaining liner material. Steel and textile cords gave the soft rubber an internal skeleton. The casing and reinforced crown were constructed separately, then joined by a transfer ring. Heat, pressure, and vulcanization locked that architecture into its working state. Inspection then searched for errors that the finished surface could no longer reveal. Our car tire is not made by filling a mold with rubber. It is built layer by layer, transformed from the inside out, and allowed to leave the factory only after its hidden structure has been checked. Every time you brake, accelerate, or turn, 4 patches of tread transfer those forces to the road. What makes that possible looks like a simple ring of black rubber. Inside, it is an entire engineered system.